Now let us try to understand about substation configuration language. So substation configuration language, that is SCL, is a description language for communication in electrical substations related to the IDs. SCL is a XML based language that allows a formal description of substation automation system, switchyard, and the relation between the automation system and the switchyard. It is also used in the configuration of intelligent electronic devices. Since XML files which are used for the IED configuration and other activities are having specific tags which are generated from the SCL language. That's why IEC 61850 language is a special language for the device configuration. Now there are various types of SCL files. So SSD is nothing but system specification description, which is an XML description of the entire system. SCD is the substation configuration description, which is the XML description of a single substation. ICD, which is nothing but the IED capability description. This gives you the XML description of the items supported by IEDs. CID is the configured IED description, which is XML configuration of specific IED. So ICD is the capability of IED, while CID is the configuration of IED. That means for a particular project or for a particular substation, the CID file will tell you that what IED can do for this particular project or substation. So now this is a sample SCL file where you will see different tags containing the various informations. So if you see the SCL file, you can easily see that this configuration is related to a relay where you are configuring the multiplier settings with minimum time and the maximum time. So similar to this, we will see lot of similar files in the substation configuration activities. Now how we do the configuration in IC 61850, we will first extract the information from a particular device which we want to configure, and then their various data points will be mapped in SCL, which will correspond to a particular object in the SCL. So for example, in this ID, the various strip commands are being connected to the digital output. So basically you are connecting the various strip commands corresponding to the individual phases, so that when the command goes, it is directly linked to the individual trips. The SCL file also describes what ID can do in a particular substation. So if you see these two XML files, so in this XML file we have the file handling capability enabled, while in the configured file the file handling is missing. So we can configure the IDs using this XML file, and what ID can do in a particular substation can be configured. Now let's see what is the use of various files which we just saw in case of SCL. So the first is the ICD file, which talks about the capability of an ID. So there might be multiple vendor devices or the vendor IDs, and all IDs will have their own specific ICDs which describe what those devices can do. So those ICD files will be imported in the system configuration tool, and then along with the SSD file and the communication configuration details, the SCD file is generated. So SCD file is nothing but the substation configuration description. So specific to a substation, this configuration tool will create the SCD file to describe the substation activities. Now this SCD file will be imported in a IED configurator, and then using IED configurator, specific CID files will be generated which are specific to the SCD file which you have imported. So using this SCD file, you will create the specific CID file for a specific ID, and then these CID files will be imported into the respective IDs. Now these IDs are configured for the activities to be carried out in a particular substation. So this is a sample SSD file. What SSD file does? So SSD file will tell you the single line diagram of a power system network, and that is represented in the form of the XML document. Now let's see the mapping of phasor measurement unit. We discussed IEEE C37.118 when we discussed the phasor measurement unit. Now, in case of IC 61850, the PMU is modeled as a logical device within an IED. So this modeling has been described in IC 61850-90-5. So here the phasors and frequency data contained in IEEE C37.118 is mapped to the measurement logical node. So if you see here in this figure, the PMU is acting as a logical device. Inside that, the measurement, that is MMUX1, is a logical node. So inside that measurement, you will have the voltage phasor and the current phasor. In voltage phasor, we will have the phasor for phase A, B, C, and then for each phase we will have the magnitude as well as angle value of the voltage. Also we will have the quality flag and the time at which the value was generated. So this information we will map using the logical node and the various data classes. Similarly, for current as well as the frequency, the information is mapped. Here, the new data object of HZ rate is added in the MMXU logical node to accommodate the rate of change of frequency data. Since in the common data classes of IEC 61850, the rate of change of frequency related object was not available. So that's why this new data object was created, and the data attribute and the quality as well as timestamp has been added to accommodate the rate of change of frequency. Now the information about the status of PMU is transmitted using the PHY health data object in an instance of the LPSD logical node. So what does it say? It will tell you the health of the phasor measurement unit, whether it is healthy, whether it is faulty, or communicating or non-communicating. So this information you can extract with the help of PHY health data object. Now the important component for the IC 61850-90-5 is the routing. Since we know that the GUs are not routable in the IC 61850, we have to create the routed GUs as well as routed sample value for the wide area applications. So in this case, since we know that IEEE 37.118 uses the standard TCP, UDP as well as IP layers for the data communication, and the GUs and sample value are not utilizing the IP and TCP or UDP layers for data communication, we need to add the TCP or UDP as well as IP layers for the data communication of phasor measurement unit data. So for that, what we have to do? We have to do tunneling. That means we will use high speed communication networks such as synchronous digital hierarchy or the SONET, that is synchronous optical network, and then we add the internet protocol layer so that the GUs can be routed. So in that case, the sample measurement value as well as GUs services are communicated via IP network. So to make them routable, we use new mapping to routable UDP, where the routed sample measurement value and routed GUs are added. So using routed sample value and the routed GUs, the information related to the phasor measurement of phasor measurement unit are shared over the network. The IEC 61850-90-5 frames are more secure as compared to IEEE 37.118 because we utilize KDC, that is called Key Distribution Center, where we can configure the keys which secure the packet transmission. So the basic difference which you will have between IEEE 37.118 and the IEC 61850-90-5 is the protocol stack. In IEEE 37.118 uses transport as well as network layers with either TCP or UDP over IP for the data transmission, while the data link layer and physical layers are left to user to choose. While in case of IC 61850-90.5, the transport and network layer are UDP over IP and link layer is Ethernet, and the physical layer is left user to choose based on the speed of communication which user wants. Security feature, we have limited security feature in case of IEEE 37.118, while in case of IEC 61850-90-5, the protocol provides a strong security mechanism by exchanging cryptographic keys among the devices using KDC. However, availability is still an issue. Now, streaming protocol is available in both. Here the streaming is done as usual, while in case of the IC 61850-90-5, we utilize routable sample value or routable GUs for the data communication. Now, average data word size in case of IEEE 37.118 is 112 bytes, while in case of 61850-90-5, the size of the data word increased to 305 bytes. Now, what are the benefits of IEC 61850? IEC 61850 normally uses the approach of Common Information Model, that is SIM, of real devices in terms of logical nodes for standardization. So because of having the Common Information Model, the data interoperability is very easy in 61850. High-level services enable the self-describing devices and automatic object discovery which will save the money as well as effort in the IED configuration as well as the IED maintenance. Standardized naming conventions with power system context eliminates the device dependencies and tag mapping. So this we have seen that how the object naming is being carried out in IC 61850, which is universal across all the IDs which are on 61850. So this helps in eliminating the device dependencies and tag mapping. Standardized configuration file formats enables the seamless exchange of device configuration. Higher performance multicast messaging for inter-relay communication enables functions which are not possible with the hardware. So since the IDs utilize multicast messaging using Goose, the information is broadcasted to all the devices which are available on the network. This helps in sending the data to multiple devices without having the hardware configuration. So because of this, the multicast messaging also enables the sharing of the transducer data to all the devices. So in this case, such as current transformer and potential transformer data, you can share with multiple devices at a time, such as the relays as well as meters, so that you need not to wire them as point to point data connection. So this makes easier for devices to receive the data from multiple transducers.